Dr. Yogesh, please share the initial slide.
Yes, ma'am.
One.
Yes, ma'am. Just a moment, ma'am. I'm just
Yes,
opening this.
certainly, certainly.
Yeah. Okay, ma'am. It is visible.
Yes, it is visible.
So again, my
Yeah.
home internet went away. I was trying to share the screen, but the internet is gone. But anyway, we will use this.
Sir, I think let Yogesh share the slide.
Okay.
Yeah, he'll change as you ask him.
Yeah,
And I
sure.
think at least it will be better. You can have
Yeah,
a
yeah.
continuous, smooth flow of the lecture.
Correct, correct.
Yes, ma'am. And
So,
recording has been started, and we are on live streaming right now. So, ma'am, yeah, now you can continue with your introduction.
Okay, okay.
Okay.
So participants, I welcome you all and the respected Professor Patrick Dasgupta, who is our next speaker of the day, to this webinar on quantum mechanics. This is part of the program Learning Physics with Conceptual and Problem-Based Approach, organized by National Academy of Sciences, Delhi chapter. Professor Patrick Dasgupta is well known to physics community, and he has already given one lecture. So I would like to introduce him once again to the participants. So Professor Patrick Dasgupta, after receiving the National Science Talent Search Scholarship in 1976, he joined BIT Pilani to do 5-year integrated MSc Physics. In 1981, he took admission in the PhD program at IISc Bangalore, but left for TIFR Mumbai in 1982 as a research scholar in theoretical astrophysics group. In TIFR, he did his PhD with Professor Jayan on luminosity functions of radio galaxies. During that period, he also collaborated with late Professor Babbage, USA, to work on quasars and galaxies. Soon after submitting his PhD thesis in 1988, he joined Ayuka Pune as a postdoctoral fellow. During 1989-90, he had short stint at the University of Wales, UK, as a senior research fellow to learn about gravitational wave data analysis techniques, as well as the observatories in Paris to have an exposure to the topic of gravitational radiation from Hull's Taylor binary pulsar. During these visits, he worked with Professor Schultz and Professor Damour, respectively. After his return, he published a paper in 1992-93 with Professor Nalikar on gravitational waves with mini creation events in cosmology. His current research interests include studies related to confirmation of Hawking area theorem from the observed gravitational waves from binary black holes, proposing a unified model for gamma ray bursts and fast radio bursts, modeling dark energy, torsion, and Chern-Simons gravity using a dynamical four-form mechanisms to generate supermassive black holes from Bose-Einstein condensation of bosonic dark matter and baryogenesis from primordial black holes. He joined the Department of Physics and Astrophysics, University of Delhi in 1993 and has been a full professor there since 2004. He has also been active in training and leading students for the International Physics Olympiad under the aegis of Homi Bhabha Center for Science Education, TIFR, Mumbai. So, sir, we extend a very warm welcome to you, and I request you to start your talk. Your PPT will be shared by Dr. Yogesh. So,
thank you. Thank you very much, Dr. Bindal.
Yeah.
So, Dr.
Yeah, yes,
Yogesh, you can straight go to the PDF page 14.
Okay.
Yesterday, I had begun discussing about inner product in linear vector space, which is essentially a generalization of the dot product that we all know from our mechanics days. And also, of course, dot product is used heavily in electromagnetic theory. So the generalization of dot product, which is called the inner product, that is a very general concept which can be used for vector spaces that are defined over arbitrary mathematical fields. But as I said yesterday, we will confine ourselves to the mathematical field of complex numbers, because quantum mechanics is based on Hilbert space, which is basically a linear vector space endowed with a inner product defined over the field of complex numbers. Right.
Sir, yeah. Can you see the screen right now?
Yes, I'm able to see the screen. So
I am here on slide number 14.
Correct. So slide number 14, the last part is where I begin the discussion on the inner product. And now we can go over to the slide number 15. Next slide. Right. So inner product basically, as I mentioned yesterday, is a mapping from V cross V to complex number, where V is the linear vector space. What it means is that you give me any vector psi1 and any other vector psi2 from the vector space V, then the inner product associates a complex number to both the vectors. In other words, the bracket psi comma chi, where psi and chi belong to the vector space, there's nothing but a complex number, and it belongs to the whole set of complex numbers. And you can do this for any pair of vectors. All right. So in other words, you can think of the inner product as a vending machine where you put in two coins. Coins are, after all, abstract wealth. They don't represent, they only are representation of wealth. They don't themselves are eatable or consumable. So this analogy, therefore, is a good analogy. So imagine inner product to be a vending machine where you insert two distinct coins, and then you get back a can of juice. Can of juice, of course, is a product which is useful for consumption. But we are now talking about the mathematical inner product, so we have to be very, very precise as to what its properties are. So we will now go to page 16, just to mention that using inner product, we can get the magnitude of a vector, we can get angle between two vectors, and so on. So therefore, inner product indeed is useful in telling us about directions of vectors. So Dr. Yogesh, can I go to slide number 16? Right. So here we are. Let's go along very systematically so that we understand the properties of the inner product very well. For every ket psi and every ket chi that belongs to the linear vector space V, the inner product, starting with ket psi comma ket chi, of course it's a complex number, but it's such a complex number that inner product ket psi comma ket chi is complex conjugate of inner product ket chi comma ket psi. In other words, if you switch the order of the vectors in the bracket, then it picks up a complex conjugation. All right. Now you might wonder, this doesn't happen in regular dot product. Of course, it doesn't happen ostensibly, but actually it is there. After all, regular dot products are based on real numbers. And in real numbers, we know for a real number, complex conjugate of a real number is the real number itself. So therefore, dot product is only a special case of inner product when the field is that of real numbers. All right. So let's go to property number 2. In property number 2, we find that if you take any ket psi belonging to the vector space V and take any two vectors which belong to the vector space V, let's say chi1 and chi2, and consider any pair of complex numbers, take the inner product of ket psi with a linear combination alpha 1 ket chi1 plus alpha 2 ket chi2. I'm just calling the vectors as ket because I'm going to introduce soon kets and bras. So I'm being preemptive in using the word ket. So take the vectors and the inner product ket psi with the linear combination alpha 1 ket chi1 plus alpha 2 ket chi2. The property of inner product says that this is nothing but alpha 1 times inner product of ket psi with ket chi1, alpha 2 times the inner product of ket psi with ket chi2. Now you can combine the property number 1 and
Sir, you are not audible. Are you there, sir? I think there is some network issue, interconnection. Uh, he has left the meeting. So there must be a network issue. So kindly wait for a minute.
again,
Yeah.
I was thrown off of the Zoom because of internet connectivity. Right.
Okay.
So as I was saying, that do consider this exercise. Please show it later that if you consider the inner product beta 1 ket psi 1 plus beta 2 ket psi 2 with ket chi, then what you will get is beta 1 complex conjugate, that is beta 1 star multiplied by inner product of ket psi 1 ket chi plus beta 2 star inner product of ket psi 2 with ket chi. Of course, beta 1 and beta 2 are complex numbers belonging to the field of C, which is the set of all complex numbers. So in other words, property 1 and 2 tells us, property 1 and 2 tell us that inner product is linear in its rightmost argument, but it's antilinear in its leftmost argument. So inner product of ket psi with alpha 1 ket chi 1 plus alpha 2 ket chi 2, you just get back alpha 1 plus the inner product with 1 plus alpha 2 inner product with 2. But if the linear combination is in the leftmost, that is inner product of beta 1 psi 1 plus beta 2 psi 2 with ket chi, then the scalars, when they come out of the bracket, they become complex conjugate of the original scalars. Right. Now let's go to property number 3. Property number 3 says that the inner product of any vector belonging to the vector space with the zero vector has to be 0. All right. All these properties are also satisfied by the normal dot product. After all, we know dot product of zero vector with any vector is 0. The fourth property is very important. The fourth property says that take any vector belonging to the vector space V, then consider the inner product of that vector with itself. That means take ket chi and take the inner product with itself. So that inner product ket chi with itself has to be greater than or equal to 0. All right, there's a general result. And in particular, if ket chi with ket chi inner product is 0, then it is necessary that ket chi is a 0 vector. Let's go to the next slide, slide number 17. Yes. So let me restate. You take any vector from the vector space. The property 4 says that the inner product of the vector with itself is always greater than or equal to 0. And it is 0 only if the vector itself is a 0 vector. So if the vector is not a 0 vector, then the inner product of a vector of that vector with itself necessarily has to be positive. Now let's consider some examples of inner product. The first example is the linear vector space formed out of wave functions that you're very much familiar with. Then consider the integral psi star of R with chi of R integrated over the entire volume. It is very easy to show that it indeed forms a genuine inner product between the wave function psi and chi. As you can see, if you take the inner product of chi of R with psi of R, obviously it will be integral chi star psi d cube R, which is nothing but complex conjugate of inner product psi R with chi R. And similarly, linearity in the rightmost argument is obvious because chi of R is sitting in the integral as it is. But antilinearity in the leftmost argument follows because in the integral, the first wave function comes with a complex conjugation. And similarly, we know that if inner product of psi r with psi r is 0, it can only happen if the wave function is 0 everywhere in the space. If it is non-zero somewhere, then obviously the integral of mod psi square d cube r always will be positive. Only it has to be, if it is 0, it can be only if psi of r is 0. Similarly, consider another vector space, C4. C4 is nothing but the vector space of all 4 cross 1 column vectors having 4 entries, and each entry has complex number. So consider 2 such column vectors, u equal to alpha 1, alpha 2, alpha 3, alpha 4, and v equal to beta 1, beta 2, beta 3, beta 4. Can I go to the next slide, slide number 18? Right. One can easily verify the inner product of u with v defined as star beta 1 plus alpha 2 star beta 2 plus alpha 3 star beta 3 plus alpha 4 star beta 4.
Sir, you are not audible. Participant, kindly be patient. Uh, because of network issue, sir has left the meeting and will join shortly.
Yeah, Again, I was thrown out. Am I audible?
Yes, sir, perfectly audible.
Yeah,
Please
yeah.
continue.
So
And sir,
this will keep happening.
sorry for interrupting you, sir. Would you like to take question in between or
Oh yeah,
at
of
the
course.
last?
If there are any
Because
questions, yeah.
yeah, there is a one question in the chat box from Akshita Goyal.
Okay,
She is
sure.
asking, does the defined inner product also follows all property of dot product like Cauchy-Schwarz inequality?
Oh
If
yes.
yes,
In fact, that is an exercise.
yeah.
I will soon give you that exercise. From the properties of the inner product, you can prove the Schwarz inequality, which says, but before that, I have to introduce the idea of norm. So just have a little bit of patience. I'll come to the Schwarz inequality. Right. Coming back to the top line of this slide, which is the definition of the inner product between two column vectors u and v, it is obvious that it satisfies all the four properties of the inner product. In particular, you can see that if u comma v is 0, it can only happen if alpha 1, alpha 2, alpha 3, alpha 4 are all 0, and beta 1, beta 2 are all 0. So u comma u is 0. So I'm saying that take u comma u equal to 0. Here u comma u will be nothing but mod alpha 1 square plus mod alpha 2 square plus mod alpha 3 square plus mod alpha 4 square. And this can be 0. Obviously, for non-zero, it is positive. But this can be 0 only if all alpha 1, alpha 2, alpha 3, alpha 4 are 0. Now, inner product can be used to define the magnitude, or as mathematicians call, norm of a vector. As from the beginning, we have been saying a vector not only has a direction, it has also a magnitude. But here is one way to obtain the magnitude of a vector. Mathematicians, of course, can find out different ways of finding out magnitude. But if you have inner product defined over a linear vector space, you can use the inner product itself to obtain the norm of a vector. And here is one way to obtain the norm of a vector. So supposing you have ket psi, a vector belonging to the vector space V, then norm of this ket psi is defined to be square root of inner product of ket psi with itself. Again, as you can see, this has been generalized from the idea of dot product itself. But you might ask, but now we are talking about a vector space over complex numbers. How do we know that square root of inner product of ket psi with ket psi is defined? The answer is very easy. Ket psi with ket psi, first of all, is always real. How does it come about? It comes from property 1 itself. Property 1 says ket psi with ket psi must be complex conjugate of ket psi with ket psi. Any number which is complex conjugate of itself must be real. So reality is established. And from property 4, we know that inner product must satisfy the condition that ket psi inner product with itself has to be greater than or equal to 0. And square root of any quantity which is greater than or equal to 0 is perfectly defined, and you take the square root, so it's nothing but absolute value, and indeed it is positive. All right. So this definition of magnitude of the vector, or as mathematicians call the magnitude to be norm of a vector can be defined using the inner product itself. Can I go to slide number 19? Yes, thank you. Here are some examples of norm. Again, go back to the standard vector space which you have been using again and again, namely the vector space formed by the wave function. You can see that norm of a wave function psi can be computed simply by taking the inner product of psi with itself which in our case is integral psi star psi dq bar. And indeed, you can use this to obtain the norm of the wave function. Now, let's make a little bit of contact with physics. After all, yesterday I mentioned that Max Born, when he analyzed many scattering experiments, he realized that the physical significance of the wave function is that mod psi square gives you the probability density in the position space. And since we know that the total probability of finding a particle anywhere in the entire universe is always one, because the particle is after all there. Unless it gets annihilated, then of course the situation changes. But a particle that is not annihilated and is conserved, that is there somewhere or other, and therefore the norm must be one, because integral mod psi square dq bar is the total probability. It should be one. And hence, in quantum mechanics, we use the normalization condition. We the uh, choose a normalization constant in such a way that the norm of a physical wave function is always equal to 1. Now let's go to the linear vector space C4, which is nothing but the vector space formed out of 4x1 column vectors with complex entries. So any vector belonging to C4 will be a column vector alpha 1, alpha 2, alpha 3, alpha 4. And again, the inner product induces a norm. So in particular, the U and V vectors we were talking about earlier, you can verify that norm of U is nothing but square root of summation mod alpha I square, I going from 1 to 4. Similarly, norm of the vector V is nothing but square root of summation I going from 1 to 4 mod beta I square. And again, you can see all the properties are trivially satisfied for the norms as well. Now, as the question had been asked considering Schwarz inequality, I will give it to you as an exercise to prove that take any two arbitrary vectors, ket psi and ket chi, belonging to a linear vector space, take their inner product and take the absolute value. Then you can prove that this is always less than or equal to the norm of psi multiplied by norm of chi. And those who are already familiar with certain aspects of derivation of Heisenberg's uncertainty principle may have already realized that the derivation hinges on the use of Schwarz inequality. But here I give it to you as an exercise to prove it. It's not very difficult to prove the Schwarz inequality, starting with the properties of inner product. Dr. Yogesh, can we go to slide number 20?
Yes.
Thank you. Yeah. So using the idea of inner product, as you can very easily guess, we can obtain the angle between any two vectors. So imagine you have two vectors, ket psi and ket chi, belonging to a linear vector space. Then the angle between them can be obtained from the cosine theta. Cosine theta is given by the inner product of ket psi with ket chi divided by norm of psi, norm of chi. By the way, I forgot to put in the numerator, you must have the modulus sign. After all, ket psi with ket chi is a complex number. Okay, so I made a typographical error there. I forgot to put the absolute value of the inner product. So please put the absolute value. And as you can see, the Schwarz inequality itself tells us that cos theta will be always less than or equal to 1. That follows from the Schwarz inequality. The mod cos theta will always be less than or equal to 1, which we know is true from our trigonometry lessons. So from this, we see that we can talk about orthogonality of any two vectors belonging to the vector space. So consider two vectors ket phi1 and ket phi2, then they are mutually orthogonal only if the inner product of these two vectors is zero. That is obvious again from the definition of cos theta angle in terms of the inner product. Right. The norm established and having the notion of angle between vectors, possible to define what is an orthonormal basis. Again, I was since I had come to the Zoom room earlier, I saw that Dr. Mamta was already talking about orthonormal basis. Orthonormal basis, they are very important in quantum mechanics. And just to give you a little bit of advanced knowledge, hopefully we will derive it tomorrow, or at least I'll make the statement, if not the derivation. It is this, that all the dynamical observables we have in nature, whether it is energy, angular momentum, or what have you can show that the eigenstates of any dynamical observable forms an orthonormal basis. The proof is long. I will only probably make a statement about the theorem because the proof will consume huge amount of time. But uh, since physics is all about observables, which can be measured in the lab, by now you must have realized science is all about quantities that can be measured, either directly measured or indirectly their consequences can be measured. Anything whose consequence or direct measurement is not possible is not part of science at all. And therefore, observables in quantum mechanics are those quantities which can be measured, and we will soon see uh, how the observables are related to the vector space idea we are talking about. But let's come back again to the orthonormal basis. Let us give the definition. So suppose you have an n-dimensional vector space V and you construct a basis. Now remember, yesterday itself we discussed about basis set. And I mentioned yesterday that there are infinite ways of choosing basis. Uh, so there is nothing unique about basis. There are infinite number of ways. After all, we know you can choose a linearly independent set in many ways. Infinite number of ways you can choose linearly independent sets. But first and foremost about basis is nothing but set of linearly independent vectors which can be used to write down any vector belonging to the vector space using linear combination. So here, imagine that you have a basis BO, which consists of vectors V1, V2 up to Vn. Remember, it's an n-dimensional vector space, and therefore the number of elements in the basis obviously has to be n. BO is said to be an orthonormal basis if and only if the inner product of ket Vi with ket Vj is the Kronecker delta Ij, where I and j are going from 1 to n. So let me again state the set ket V1, ket V2 up to ket Vn is said to be an orthonormal basis if and only if the inner product of ket Vi with ket Vj is a Kronecker delta Ij. That means what? When I is equal to j, then delta Ij is of course equal to 1. That means ket Vi inner product with itself is 1. That means all the ket Vi's have norm equal to 1. And if I and j are not equal, then of course the Kronecker delta ij is 0. That means ket vi with any other ket vj, these two are mutually orthogonal. So therefore, an orthonormal basis consists of vectors which are mutually orthogonal to themselves. Furthermore, each of the vectors, their norm is unity. That is, norm of ket vi is 1. So such a basis is called orthonormal basis. Now some examples. So let's go to the normal dot product. After all, by now, I'm sure you would have convinced yourself that the dot product concept is a special case of inner product. That is, whenever the inner product is defined over n-dimensional Euclidean space over the field of real numbers, then inner product just reduces to the dot product. And in particular, example A is about the three-dimensional Euclidean space R3. The three-dimensional Euclidean space is called R3 because there are three axes, each axis represented by real numbers. So it is R cross R cross R, and hence it is called R cube. And we know that one particular orthonormal basis for the Euclidean space is the unit vector I, unit vector j, unit vector k. Similarly, if you go to C3, which is the 3 cross 1 column vector
Sir, you are on mute. Sir has again left. Please wait.
again I was thrown out.
Yeah, sir.
Am I audible?
Yeah, sir.
Am I audible?
Audible.
Yeah.
Please
Yeah.
continue.
Okay, so for C3, one particular orthonormal basis can be chosen to be first column vector being 1 in the topmost entry, 0, 0 in other rows. Similarly, 0 in the first row, 1 in the second row, 0 in the third row, and 0, 0 in the first and second row, and 1 in the third row. You can easily verify that any vector alpha, beta, gamma, so any column vector, 3 cross 1 column vector alpha, beta, gamma, can be expressed as alpha into 1, 0, 0 plus beta into 0, 1, 0 plus gamma into 0, 0, 1. So that means that you can express any 3 cross 1 column vector as a linear combination of these three basis vectors. Now, a quantum mechanics example, you have all solved exactly the energy eigenfunctions of the Hamiltonian corresponding to hydrogen atom, and you all know that the angular part of the wave function energy eigenfunction is nothing but the eigenfunction of the L square operator, where L square is the square of the orbital angular momentum operator, and that eigenfunction is the spherical harmonics ylm theta comma phi. Ylm theta comma phi is nothing but PL cos theta times e raised to power I m phi, where PL cos theta are the legendary polynomials. These are something which you have already done. I am just summarizing for you the result, and you have the Laguerre polynomials R and L. So the Laguerre polynomial multiplied by the spherical harmonics, this forms orthonormal basis for the entire linear vector space consisting of wave function psi of r. So this is an example of what I stated, that is the eigenfunctions of Hamiltonian form a orthonormal basis. Dr. Yogesh, can I go to the next slide, slide number 22?
So we are on slide number 22.
Yeah, so slide number 22, we now consider a very important topic And this is one topic where we will go slow. We'll try to understand every little bit. And this is the idea of Dirac's bra and ket. The idea is actually very simple. So remember, we have already talked about inner product of two vectors. So take the vector ket psi, take another vector ket chi, and the inner product we are writing it as bracket ket psi comma bracket ket chi. What Dirac did was that he realized that after all, I can split the bracket into two. So look at equation number 6. Dirac wrote the inner product of ket psi with ket chi, the angular bracket psi followed by chi with the angular bracket. And now he utilized the fact. Now this is very important. Just know from the property 1 that alpha 1 ket chi 1 plus alpha 2 ket chi 2 is nothing but alpha 1 inner product of ket psi with ket chi 1 plus alpha 2 into inner product of ket psi with ket chi 2. So Dirac, in his notation, therefore, he is saying that the angular bracket psi acting on ket alpha 1 chi 1 plus alpha 2 chi 2 is nothing but alpha 1, that angular psi acting on ket chi 1 plus alpha 2, the angular psi acting on chi 2. Dirac said that look, this object, because I have split the bracket into two parts, the first part I will call bra, the second part I will call ket. The first part, which angular bracket starts first, followed by psi and the vertical line. This object I will call as a strange abstract object called bra. And the inner product is nothing but this bra acting on a ket chi. So in other words, let's go back. So this is a very important. So remember, it is playing around with the notation and from the property of the inner product, arriving at a notion which is fundamentally very novel. And Dirac, throughout his life, he kept on doing it. He had a fantastic sense of mathematical beauty, and he would pull mathematical ideas from nowhere and apply to physics and get astoundingly beautiful result. Like, for example, how when he tried to take the square root of the Hamiltonian and got into negative energy and spin half particle, or using a non-singular vector potential to talk about magnetic monopoles, or using a time-dependent Newtonian gravitational constant to talk about a different kind of cosmology. Dirac was a master of using abstract mathematical ideas but applying it to the physical world in a very novel manner. Introduction of bra is an illustration of it. So let's go very slowly. So what is Dirac doing? Dirac is writing the inner product of ket psi, a vector with
Sir, you are not audible. Kindly be patient. Sir will come back shortly. Yes, he is here.
Yeah, again I was thrown out. Am I audible now?
Okay, sir, you are audible. Please continue, sir.
Yeah. This will, with a probability, quantum mechanical probability, I'll continuously get thrown out of the. I hope I'm not permanently thrown out, but I trust quantum mechanics that I'll not be permanently thrown out. Okay, yeah. So as I was saying, that so Dirac used this idea of writing the inner product with angular bracket, and he took the first part as a strange kind of animal called as brassi, and interpreted the inner product as this brassi acting on the vector ket chi to produce a complex number. What is that complex number? This complex number is nothing but the inner product of ket psi with ket chi. So what Dirac is therefore doing is that from the inner product of ket psi with ket chi, he is abstracting out a brassi out of the inner product. So brassi is a strange animal, and brassi acts on ket chi to give nothing but the inner product of ket psi with ket chi. So earlier, people were thinking that inner product can be thought of as a product between two vectors. Dirac, with his notation, is saying, no, I can also interpret it. I can interpret the inner product as a strange animal called brassi acting on ket chi to produce my inner product. So this is a new interpretation. And you can think of the bra, I will give it to you as an exercise to prove that set of all bras themselves form a linear vector space. So this vector bra can be thought of as an abstract machine that eats up an abstract vector like ket psi or ket chi and regurgitates out a complex number. So a bra is a machine which eats up a ket psi and throws out a complex number. All right. So this is one pictorial way of thinking about bras. But by this time, we must have realized, well, all this nice pictorial words for memory's sake or for the purpose of creating interest is fine, but one has to be very, very precise in physics and mathematics. So let's go into the properties of these bras. The first property is every bra, let's say bra phi, can I go to slide number 23? Yeah. So every bra is associated with the corresponding ket phi. And how does it come about? Obviously from the definition of the bra itself. So a bra phi acting on ket psi by definition is inner product of ket phi with ket psi. So in other words, you give me a ket phi, I will give you a bra phi. And how will I give you a bra phi? You have given me ket phi. I'll produce a bra phi to be such an object that when it acts on ket psi, the complex number you get is nothing but inner product of ket phi with ket psi. It is as simple as that. What is the other important property? And that follows from the linearity property of the inner product. We know that inner product of ket phi with the vector beta 1 ket psi 1 plus beta 2 ket psi 2 is nothing but beta 1 inner product of ket phi with psi 1 plus beta 2 inner product of ket phi with ket psi 2. And in Dirac's notation, therefore, this inner product is nothing but bra phi acting on a state. That ket vector state is beta 1 psi 1 plus beta 2 psi 2. And using the linearity property, we know that the bra phi acting on beta 1 ket psi 1 plus beta 2 ket psi 2 is nothing but beta 1 bra phi acting on ket psi 1 plus beta 2 bra phi acting on ket psi 2. So in other words, the bra phi object is a machine that is linear in its action on kets. So bra phi, of course, is something that acts on the ket psi, but it acts as a linear object. Mathematicians call such objects as linear functional. So mathematicians defines something called a linear functional. A linear functional is nothing but a mapping from vector space to field F. Of course, in our case, the field F is the field of complex numbers. So mathematicians define linear functional as a mapping from the vector space to the set of complex numbers. And bra clearly is an example of a linear functional. And it's linear functional because of this linearity property which we have just outlined. Are there any questions regarding bra? Because very often students who are getting exposed to ket and bra vectors, they have a lot of questions regarding these concepts. So this is
yes.
the right time to pause. If there is any question, you can ask.
Yes, sir. There is a question from Anurag Mishra.
Yeah.
He's asking, please explain again bra and cat. I think he's confused in the term
Sorry?
bra and cat. Please explain again bra and cat.
Okay. Yeah. So let's go back. After all, we have already seen how to take the inner product. So you take any vector, let's say ket phi belonging to the vector space V and ket psi belonging to the vector space V again. So we know how to take the inner product of ket phi with ket psi. We have been our inner product parenthesis, that is the usual bracket. We say the inner product for ket phi and ket psi to be parenthesis open, ket phi, comma, ket psi, and then parenthesis closed. But that is our way of doing it. What Dirac did was, he, instead of using parenthesis, he used angular bracket to denote the inner product. So if you have two vectors, phi and psi, Dirac would say that my inner product is angular bracket phi with a vertical line between psi. And then Dirac said, well, can I interpret this inner product instead as action of an object, abstract object called bra phi, that is angular bracket beginning followed by phi and then the vertical line. I will say that this is a mathematical object. I don't know what that mathematical object is. All I will say is that this mathematical object is such that when it acts on vectors like ket psi, it produces the inner product of ket phi with ket psi. Remember, inner product of ket phi with ket psi is involving two vectors, ket phi and ket psi. But Dirac said that, can I think of this inner product not as a product between two vectors, instead as some object called bra phi acting on a vector and producing a complex number. So you will ask, but okay, if there's a abstract object acting on ket psi producing a complex number, what is this complex number? Dirac would say the complex number is precisely inner product of ket phi with ket psi. So Dirac automatically is saying that for every ket phi, there is a strange mathematical object called bra phi, such that bra phi acting on ket psi is simply the complex number obtained by taking the inner product of ket phi with ket psi. All right. So you're introducing a new object altogether out of thin air. But then there must be some usefulness of that object. Why did you generate such a mathematical object? We'll come to that too, slowly. So, Anurag, are you following me? Is there any question?
Yes,
if there's
sir.
any question, you can
Yes,
ask me further.
He understood, sir.
All right, all right.
Okay,
But
sir.
what is, yes, are there more questions?
Yes, sir. There are another question from Akshita.
Yeah.
What does the phrase axon mean in physical term?
Yeah, a good question. So let's go back to something we already know from our old physics and mathematics courses. When you take a function f of x, then we can say, let the derivative act on the function f of x. So what does one mean by saying derivative acting on function f of x? We say d by dx of f of x. So the word or the phrase acts on in the case of derivative is nothing but, if I am saying a derivative acts on a function f of x, then I get a new function. After all, we know d by dx of f of x is another function. So similarly, here acts on meaning we have an abstract mathematical object we are calling bra phi. When I say it acts on ket psi, all it says is bra phi. When I place it next to a ket psi, what I get is a complex number. So that is the phrase acts on meaning. So have I cleared you, Arpita? Your question?
Akshita, okay, yes, sir, she got it.
Are there any
Yeah,
other question?
yeah. There is a last question from Ayushi. How can we understand dual space physically?
Exactly. So I'm coming to dual space now. Okay. So yeah, before I come to the dual space, I must highlight one of the most important property of the bra vector. I mentioned it, but there is no harm in mentioning it again. The bra vectors are such that they act linearly on ket vectors. So in particular, bra phi acting on beta 1 ket psi 1 plus beta 2 ket psi 2 is nothing but beta 1 into bra phi acting on psi 1 plus beta 2 bra phi acting on ket psi 2. Of course, this follows from the definition of the inner product itself. Now, the exercise, yeah, I leave it to you to do this exercise. Please show that if you take the set of all bras, then it forms a linear space. So starting with the definition of bra, yeah, yes, after all, zero vector is there, and zero vector inner product with any ket psi, we know from the properties of inner product, is always zero. So therefore, the zero vectors, its bra is nothing but the so-called zero bra. All right. Now, uh, uh, I will confine myself to dual vector space for quantum mechanics, but the mathematicians have much more generalized definition of dual spaces, because they also have dual spaces, spaces in differential geometry, etc. But since this lecture is all about quantum mechanics, I will stick to the dual vector space corresponding to the linear vector space that occur in quantum mechanics. So go back to the exercise. Consider the linear vector space formed out of all such bra size. This vector space, as I have given you exercise, itself a linear vector space. And such a linear vector space is denoted as V star and called dual vector space corresponding to the vector space V. Of course, it is associated with vector V. Why is it associated with vector V? After all, it is constructed out of ket psi, because for every ket psi, there is a bra psi. So the dual vector space itself corresponds to the vector space V. Now, the question was, what can we think about the physical association of a dual vector space in quantum mechanics? The answer is yes. I will show you an example. Just like you have your vectors, which can be represented as column vectors, we will soon see that the corresponding dual vector is a row vector with all entries complexified. That is, you take the complex conjugate. So if you have a vector, column vector, alpha 1, alpha 2, up to alpha n, then the corresponding bra vector is nothing but the row vector alpha 1 star, alpha 2 star, and so on. In other words, the bra vector is nothing but taking a vector. After all, you know how to take the adjoint of a vector. What you do is transpose the vector and take the complex conjugate. This is something you have been doing when you have learned matrices, how to take the adjoint of a matrix. So adjoint of a alpha 2 up to alpha n is nothing but the row vector alpha 1 star, alpha 2 star, up to alpha n star. So
I think there is a network issue, so please wait.
again, I
Is
was
that?
thrown out of Zoom. Am I audible now?
Yes, sir, you're audible.
Yeah. So to complete what I was saying, the one way to see the usefulness or significance of bra vectors is that, as we will see, that you can always choose a basis in which any linear vector can be written down as a column vector, and therefore the bra vector corresponding to such a column vector is nothing but adjoint of this column vector. In other words, you make complex conjugation of the entries and make the column vector a row vector. Okay. So let's come to the examples of bras. And the question was at the right moment, because precisely the same example I'll give you. So consider the linear vector space C4. C4 is nothing but, can I go to slide number 24? Yeah.
Yes, sir, we are on.
Yeah. So consider the space of all 4 cross 1 complex column vectors, which is called C4. And of course, it's a linear vector space. And consider two vectors, U and V. U is alpha 1, alpha 2, alpha 3, alpha 4. And V is beta 1, beta 2, beta 3, beta 4. Then we, of course, know that this is something we have already encountered before. We all, of course, know that the inner product of U with V is nothing but summation I equal to 1 to 4 alpha star beta I. But the same thing can obviously be obtained by multiplying the row vector. Look at equation 8. So take the row vector alpha 1 star, alpha 2 star, alpha 3 star, alpha 4 star, and do the matrix multiplication of this row vector with the column vector beta 1, beta 2, beta 3, beta 4. And then you will just get alpha 1 star beta 1 plus alpha 2 star beta 2 plus alpha 3 star beta 3 plus alpha 4 star beta 4. So you can see that you have got the inner product of UV by just taking the row vector acting on the column vector, the row vector alpha 1 star, alpha 2 star, alpha 3 star, alpha 4 star, acting on beta 2, beta 3, beta 4. This is what exactly a bra vector is supposed to do on a ket vector. And again, it is easy to prove that the space of all such row vectors as defined by equation 8 indeed forms a linear vector space. Can we go to slide number 25? Right. Now we will take up the most important topic as far as quantum mechanics is concerned. The topic is about the linear operators. So what is the linear operator? Consider two vector spaces, linear vector spaces, V and W. Then linear vector space is nothing but a mapping from the vector space V to the vector space W. All right. And in a elaborate manner, what this is telling you is that if you take the vector, one moment, I'm just if you take the vector ket psi, any vector ket psi belonging to the vector space V, then the linear operator acting on ket psi is an element of W. So again, let us be very, very careful as to what we are saying. So we are given two linear vector spaces, V and W. Then a linear operator A is defined to be a mapping from vector space V to W. And what does this mapping do? It takes any ket psi belonging to the vector space V and associates a vector which belongs to vector space W. Remember, A acting on ket psi is not an element of V. It is an element of W. But then there are two very important properties a linear operator must satisfy. And what is it? Take any vector belonging to the vector space V and take any scalar from the complex number. So let alpha be any scalar from the set of complex numbers. The linear operator must satisfy the following, that after all, V is a vector space. If ket psi is an element of vector space V, then alpha times ket psi is an element of vector space V. The second property says A acting on alpha times ket psi is nothing but alpha times A acting on ket psi. All right. So physically what it means is that if I have a vector and another vector which is twice the original vector, then A acting on twice the original vector is twice A acting on the original vector. So this is what the second property is asking to be satisfied. Third property is, let us take any two vectors ket psi 1 and ket psi 2 belonging to the vector space V. All right. Because V is a vector space, if ket psi 1 and ket psi 2 belongs to vector space V, ket psi 1 plus ket psi 2 also belongs to the vector space V. All right. Therefore, the third property demands that a linear operator acting on ket psi 1 plus ket psi 2 will be linear operator acting on ket psi 1 plus linear operator A acting on ket psi 2. So second and third properties essentially is elaborating on the linear nature of the mapping. Again, the examples are something which you have encountered again and again. The first example, I suddenly realized that other examples have not been put in the PDF mode, but doesn't matter. They are something which you are already familiar with, so I can talk about them just in words. Well-known examples are the differential operator grad and Laplacian operator grad dot grad. These are operators you're familiar with from your electrodynamics course themselves, but in standard wave function approach quantum mechanics, you know that grad can act on the complex wave function psi of r, del square can act on complex wave function psi of r, and these are linear operators. That is, grad acting on alpha psi of r will be alpha grad acting on psi of r. Similarly, Laplacian operator del square acting on alpha psi of r is also alpha Laplacian operator acting on psi of r. So linearity is trivial to establish for these operators. What are the other operators that you're familiar with? I think, let me check. Yeah, slide. Yeah. So if you go to the next slide, so other examples are, consider the complex uh, vector space Cn. Cn is nothing but the vector space formed out of n cross 1 column vectors with complex entries. What can you imagine a linear operator to be for this space? Obviously, n cross n matrices. We know that when any n cross n matrix, and the entries in the matrix can be any complex number. So take any n cross n complex matrix, then it can act on a column vector alpha 1, alpha 2 up to alpha n. And by the procedure of matrix multiplication, n cross n matrix multiplied by n cross 1 matrix, you know what are the entries. You will get another column vector. So indeed, it's a linear operator because if I take alpha into, any other complex number c into alpha 1, alpha 2 up to alpha n and a matrix act, the c will simply come out and the matrix will act on alpha 1, alpha 2, etc. Now, you see, that is the power of mathematical abstraction. Now I will argue the bra phi ket, ket phi bra chi is actually a linear operator. Now see how a mathematical imagination of Dirac gives us a very weird kind of a linear operator. So consider the following strange animal constructed out of ket phi followed by bra chi. I will argue that this object, ket phi bra chi, is actually an operator. Why is it so? First of all, if it is an operator, then if it acts on any state, ket chi, it must produce another state. By the way, this linear operator is between the vector space V to V. All right. From now on, when we talk about linear operators, we will talk about linear operator, which those are mapping from vector space V to itself. We'll not consider separate vector space. After all, in quantum mechanics, the linear operators will only act on the space of physical states, which is the Hilbert space, and take them to the same Hilbert space. So let's come back to the example C. Oh, I have made a typo. It's not D, but example C. So example C is, I will argue that the object ket phi bra chi is actually an operator. Why is it so? Because ket phi bra chi acting on ket psi is nothing but ket phi bra chi acting on ket psi, but bra chi acting on ket psi is nothing but inner product of ket chi with ket psi, which is a complex number beta. So in other words, what this tells you is the object the object ket phi bra chi acting on ket psi is nothing but a complex number beta multiplied by ket phi, where the complex number is nothing but bra chi acting on ket psi, or in other words, inner product of ket chi with ket psi. All right. And later on, if I have time in either tomorrow's lecture or day after tomorrow's lectures, I will show that all physical observable can be actually expressed as summation of eigenvalues of those observable multiplied by ket eigenstate, bra eigenstate. So the example C is a particular case. In fact, all observables can be written in terms of linear combination of ket psi I, bra psi I. All right. So you see that Dirac's mathematical imagination gave us a new mathematical structure that would enable analysis in quantum mechanics in a much elegant fashion. You might now ask that, well, what have all this ket psi to do with the wave function which we are talking about? Before we encountered ket psi's, bra psi's, we were doing quantum mechanics very easily using wave function, which were complex functions. After all, you have solved one-dimensional rigid big box problems, and you get the eigenfunctions as sine n pi x by L length of the box and so on. You have got the hydrogen atom eigenfunctions RNL, YLM, theta phi. How are these related to the ket psi abstract states that we are talking about? So since we have already almost covered 1.5 hours, I will take the details in tomorrow's lecture. But sorry, let me give the result as to how the wave function psi of R are related to ket psi and the basis vectors, which are eigenvectors of the position operator. So as I said, that all dynamical variables, all physical variables correspond to a particular kind of linear vectors. They are called Hermitian vectors, sometimes also referred to as self-adjoint linear operators. We will discuss all this tomorrow. And in particular, if you take the position operator, then the position operators have position eigenstates and corresponding position eigenvalues. Psi of R, the wave function psi of R, is nothing but inner product of the eigenstate ket R with ket psi. You can ask, can we think of inner product with eigenstates of other observable? Yes, if you take the momentum eigenstates ket P, momentum operator, abstract momentum operator, then the momentum wave function, take the same ket psi, take the inner product of ket momentum eigenstate ket P with ket psi, what you get is psi tilde of P, which is the momentum eigenfunction corresponding to position basis eigenfunction psi of R. And you have already worked it out, how to get momentum wave function from position wave function. You do it by doing a Fourier transform. And all this comes very naturally from this abstract linear vector approach that we will do it tomorrow. But in the remaining time, because today's topics were somewhat unfamiliar, I think, for most of the undergraduate students, I think we should spend more time taking questions so that these concepts are clarified. And only when all such concepts are clarified, we will talk about details of linear operators. What is a Hermitian or a self-adjoint operator? And already I think Dr. Partha Goswami has proved that the eigenvalues of Hermitian operators are always real. So we will not undergo that proof. Maybe I will only prove that if you take two distinct eigenvalues, the corresponding eigenvectors are mutually orthogonal. That proof probably I will do most probably in tomorrow's lecture. But I would suggest that we have a lengthy question answer series now. Yogesh, are there questions?
Yeah, there are two questions in the chat box.
Okay.
First question, for del and del square, on what space omega is the mapping done?
Yeah, so as I said, the mapping in the example I took, the mapping is the linear vector space of wave function. So V is the linear vector space of the wave function, and W is the same vector space. W is also the vector space of complex wave function. So del and del square act on complex wave function to produce another complex wave function. As an example, if I take the del operator and act it on a momentum eigenfunction, the plane wave, which is by now you're already familiar with such momentum eigenfunctions like plane wave, which is some constant into e raised to power I p dot r divided by h bar. So take this object a into e raised to power I p dot r by h bar, which is an eigenfunction of the momentum operator minus I h bar grad operator, right? Now apply the grad operator on such an object, that is a into e raised to power I p dot r by h bar. What will you get? You will get, you can easily see what you will get is I into vector p divided by h bar into the original eigenfunction, right? So you're again getting back a complex wave function, but it is different because now it is I by h bar into the vector p multiplied by the original eigenfunction. Obviously, from this, you can see that minus I h bar grad, if it acts on a into e raised to power I p dot r by h bar, you will simply get the momentum eigenvalue p into the eigenfunction. And that's the reason why it is the eigenfunction. You get back the eigenvalue p. So have I answered your question?
Akshita, it is clear to you? Please respond. Yes. She got her answer, sir. Next
Right.
question is from Anurag Mishra. What are
All
the
right.
applications of these operators with wave functions? What we get by applying these operators?
Yes. So as I said, although this will be detailed tomorrow, as I said, all dynamical variables, you think of any quantity that you can measure in the laboratory. For every quantity that you can measure in the laboratory, there is a Hermitian linear operator. All right. This is one of the postulates of quantum mechanics, and it has come out of experiments. And therefore, unless you mathematically know the nature of these Hermitian operators, which correspond to measurable quantities in the laboratory, what are the values that you are going to get? To give you an example, take the hydrogen atom. Okay, so you take a jar of hydrogen gas, and let's say this hydrogen gas is at room 30 degrees centigrade. If you did not know the Hamiltonian operator for the hydrogen atom, you will never be able to predict that if I heat up the hydrogen gas, what spectral lines would I see when I pass the radiation emerging out of the hot hydrogen through a prism. You'll not be able to predict. So the lines which you see when you take a very hot hydrogen gas and the intense white light coming out of very hot hydrogen gas, when you pass it through a prism, you see various lines. How do you explain the lines? These lines are nothing but the difference of the energy eigenvalues of the Hamiltonian of the hydrogen atom. Of course, what I have said is how all these things were discovered. First, spectroscopists uh, observed all these discrete lines, the so-called Balmer lines, Paschen lines, Lyman lines, and people were completely flabbergasted. Where are the lines coming from? Classical theory will give you continuum of radiation from a hot gas, but why am I seeing discrete lines? Later on, Niels Bohr explained using the atomic model, but Niels Bohr's model was old quantum theory, having lots of ad hoc assumption. But then Heisenberg used matrix mechanics to explain, and it emerged that the lines are nothing but differences between eigenvalues of the Hamiltonian, which are the energy eigenvalues. Similarly, if I am doing electronics with semiconductor physics, and I want a band gap between the valence band and the conduction band and so on, all these band gaps arise by solving the eigenvalues of the Hamiltonian describing the crystalline semiconductors. So these are not just abstract ideas, they are again and again being used to develop all kinds of surprising semiconducting materials or nanomaterials, which are being used in all kinds of sophisticated devices like mobile phone and various detectors, etc. So without quantum mechanics, these things cannot be understood. You cannot guess what kind of new devices you can make without the use of quantum mechanics. In fact, the whole area of nanomaterials came out of thinking about quantum mechanics of fewer than a few thousand atoms. Nanomaterial first was theoretically understood, and then came the experimental corroboration. And we are now waiting for second and third revolution that is going to change human civilization, namely the emergence of quantum computation, where your bits will not be just 0 bit and 1 bit, but you can superpose ket 0 bit with ket 1 bit and so on. And similarly, teleportation of states. One can teleport a quantum state from here to another place almost instantly. By the way, all these, they don't violate special theory of relativity because you're not transferring physical material. You're just transferring an idea of a state from one place to another place with almost instantly. So these are going to be practical soon. But right now, theoretical work has already been showing bright and a surprising result. And it is only going to be few years from now when experimentalists will achieve it. So if you think that all these are mathematical and have no applications, then clearly that is not the case.
Sir, I think he has understood his question. Uh, Next question is from Anudeep. Which interpretation of quantum mechanics do you subscribe to?
But that's a, okay, let me tell all the other students what the problem is. I had alluded this problem to yesterday even, as I said, that um, Schrodinger equation is a deterministic equation. It takes the wave function of a particle and it evolves it in a deterministic fashion, because the solution you get by solving the Schrodinger equation, I h bar del by del t of psi equal to Hamiltonian operator acting on ket psi. So you might ask, if Schrodinger equation solves the wave function in a deterministic manner, where are the probabilities coming in? After all, measurement, when you take a quantum system and you measure it, what is measurement? Measurement is nothing but a measuring apparatus interacting with the quantum state. But any interaction is uh, conveyed by a Hamiltonian operator. So even measuring apparatus probing a quantum state is nothing but through a Hamiltonian, and therefore the combined state will evolve according to the Schrodinger equation, and it should evolve deterministically. Why should there be a probability? And as Schrodinger had given a picturesque description of this process of measuring apparatus interacting with a quantum system in using his famous cat paradox. Imagine cat is the measuring device which is linked with a quantum system which can be in two states. And let's say the two states are ket1 and ket2. Okay, so your state, quantum state, is a superposition of ket1 plus ket2. And when the cat interacts with ket1 plus ket2, interaction is a Hamiltonian interaction. And the Hamiltonian interaction, let's say you have arranged in such a way that if the state is ket1, then cat dies. The state of the cat is dead cat state. While if the state is ket2, then the state of the cat is live cat. So when you interact the cat with this ket1 plus ket2, what Schrodinger equation will give you is cat dead multiplied by the state cat dead multiplied by ket1 plus cat alive multiplied by cat2. But in the real experiment, you don't see this entangled superposition. What you see is either cat is dead and the state of the quantum system is ket1, or cat is alive and the state of the system is cat2. I could have shown you the picture because I'm not able to share the file. All these are part of my file, but maybe in this.
So I hope she got her answer. Sir, there is a last question from Abhiram. He's asking, he always use linear wave function or linear vector space, etc. Does the nature gives always linear wave function? Sir, can you hear me? I think sir again uh, left. So please wait for a minute. He will be back soon. There is some network issue at their end.
Yeah, students, you have to have some patience. He'll join back soon.
Hi, I was again thrown out. Am I audible now?
Yes, yes, sir. You are audible now.
Till which part was I audible when I was talking about the Schrodinger cat paradox?
Okay, sir. Can I repeat my question again?
Please repeat the question.
Sorry?
Which you were asking.
Can I repeat the question again?
Yeah, I mean, the entire part was not audible at all when I answered.
No, you were audible till you were talking about cat paradox, etc. So he was reading the question, next question, when we lost him.
Yeah. So the question was about which interpretation of quantum mechanics I favor. And in this regard, I was giving you an example of cat being the measuring apparatus. So when it interacts with a quantum state, which is a superposed state ket1 plus ket2, the arrangement is such that when cat as a device interacts with ket1 plus ket2, then if ket1 part interacts with cat state, the cat state becomes cat dead state. While if ket2 part interacts with the cat state becomes remains cat alive state. So therefore, Schrodinger equation will predict that when the cat as a measuring device interacts with ket1, when cat as a measuring device interacts with the quantum state ket1 plus ket2, Schrodinger equation predicts that the outcome would be the state cat dead into ket1 plus the state cat alive into state 2. So Schrodinger equation gives you an entangled state. But in real world, we know when you do the experiment, Either you see the cat dead and quantum state ket1, or you see cat alive, quantum state ket2. And this happens in a probabilistic fashion. When you repeat the experiment, sometimes you will see cat dead ket1, sometimes you will see cat alive ket2. And where the probability comes from, no one knows, except Born just gives Max Born gave a rule how to calculate the probability. But in strict fashion, there shouldn't be probability, because any measurement is, after all, a Hamiltonian interaction. So this problem about where the probability comes from is the so-called uh, theory of measurement in quantum mechanics. And the question was about um, I don't want the visual. The question was about, because the visual thing eats up the bandwidth, I'll again be thrown out. So the question was about which interpretation I favor. I actually favor the many world interpretation, which says that every time there is an interaction, the Hilbert space states get split up. So you have infinite number of copies of the world. So when I'm doing the cat experiment, I'll be in a different world where I'll see the cat is alive, state is 2. There'll be another copy of mine which will see cat is dead, and the quantum state is ket1, and so on. But as everyone knows, the jury is still out. We still, more than 100 years have passed since the birth of quantum mechanics. Great physicists like Einstein, Bohr, Heisenberg, Schrodinger, many people have uh, worked on this. I myself, as I tell many students of mine, wasted without showing anything worthwhile about how to get this measurement problem. Wasted many hours of my work thinking about the problem. Um, and the jury is still out. One really doesn't know uh, what causes this probability. But if you ask me uh, as to do I have a guess as to what causes the so-called collapse of the wave function and the probabilities, uh, I will say my guess is it is large number of particles belonging to a measuring apparatus and associated gravity. I would say that is um, uh, that is what is the real cause of the collapse of a wave function and the probabilities appearing out of the many world situation, when the number of subsystems are very large of the then you have this collapse, and gravity might be playing a very important role. But these are all my speculations. The jury is still out.
Uh, so I think it is clear. Uh, Next question is from Abhiram. He's asking, we always use linear wave function or linear vector space, etc. Does the nature gives always linear wave function?
Well, there is a series of papers that was written by Steven Weinberg in, I think, 90s, where he said that, look, linearity, uh, how good is the linearity in quantum mechanics? And you introduced a parameter to check whether at some level there is a nonlinearity. It's an important question, because maybe it is some tiny nonlinearity which is causing this probabilistic outcome. After all, in classical uh, dynamical theory, we know nonlinearity can lead to chaos, and chaos can lead to unpredictability. So if there's a tiny nonlinearity that is introduced, could that explain collapse of wave function into probabilities? But uh, uh, Weinberg's work were uh, collated with a lot of experiments. The precision with which linearity works is phenomenal. So, to great precision, we can say that quantum mechanics is based on complete linear vector space with unitary evolution of the wave function according to Schrodinger equation. Have I answered your question, Aviram?
Anurag, please respond. Abhiram, please respond. Did you get? Yes. He got his answer, sir.
Okay, okay.
Sir, next question is from Akshita. She's asking this question in concern of cat paradox. And
Right.
she's asking, does it mean that probability of obtaining a particular state only become apparent when we do the experiment repeatedly?
Yeah, so, okay. First thing is that the probability can be calculated using the Born rule. So if you have a state ket psi, and if your measurement produces, makes the state ket psi collapse to one of the eigenstates, let's say ket ai, then Born rule will say the probability that ket psi will collapse to ket I is given by bra ai acting on ket psi, or in other words, inner product of ket ai with ket psi, take the inner product and take mod square of it. That'll be the probability. So quantum mechanics formalism and the Born rule will give you a theoretical answer for the probability. But how do you know that this theoretical answer is correct? And to verify whether the Born rule is correct, you have to take an ensemble of identical quantum systems, with each quantum system having the identical quantum state ket psi, and then perform on each of this quantum system. That means there's an ensemble of observers using identical measuring apparatus and operating and doing the measurement on this ensemble of states, and finding out the frequency with which they get different eigenvalues, and compare the frequency of the eigenvalues with the Born rule probability. And so far, experimentally, one has seen that Born rule indeed uh, is confirmed from millions of experiments. In fact, the entire particle physics set of experiments like LHC, etc., they keep confirming the whole idea of Born rule and the associated probability. Have I answered your question, Akshita?
Yes, sir. She replied. She got her answer. There is a next question from Arya. Is time-dependent perturbation based on linear or non-linear wave function?
No, there is nothing called, no, wave functions are neither linear or non-linear. Linearity is associated with the operator and how the system evolves. Whether you take time-dependent or time-independent perturbation, the whole of quantum mechanics is linear. There is nothing non-linear about the structure of acting on states. So quantum mechanics is totally based on linear vector space approach. Whether it is time dependent or time independent perturbation, or whether it is quantum field theory describing different elementary particles, or whether electroweak theory with Higgs mechanism, as far as evolution of states are concerned, you use linear vector space with unitary evolution that follows from Schrodinger equation. Have I answered you, Alia?
Yes, sir. She understood and got her answer. Sir, I think this is the last question of this session from Vara Lakshmi.
Okay.
If nature gives linear wave function, whatever
No. I must again correct. There's nothing called linear wave function. You have a linear wave vector space.
Sir,
Wave function is only a member of linear vector space.
Okay. Should I repeat,
Yeah,
sir?
yeah. Please repeat the question.
If nature gives linear wave function, whatever we are seeing wave in ocean is as it fall as linear wave function.
Sorry, whatever, I missed out the middle part. Can you repeat
Uh,
the question, please?
so whatever we are seeing waves in ocean
Yes.
is as it fall as linear wave function.
Wait a minute. See, the waves in the ocean, they are classical waves. They are made out of much more than Avogadro number of quantum systems. So the waves you see, the waves, even in the waves in a pool, water waves in a pool, they're all classical waves. And classical waves, uh, when the amplitude are high, they can be nonlinear. After all, uh, you have solitonic wave solution where the evolution is based on a nonlinear equation. These are classical systems. Quantum systems always obey linearity as the basic structure in its mathematical formalism.
Okay, sir.
That was the last question, no?
Yeah, this was the last question. I think there is no more question in the chat box.
Yes.
And thank you so much, sir. You have handled all the queries very well. So now I request to
Thank
Pushpa
you.
ma'am.
Yes, sir. So thank you so much, Patrick sir, for giving
Most welcome,
such a
Dr.
nice
Pushpa.
talk. Such a nice talk. You have always explained the concept so well. So thank you so much for giving this talk, and we look forward to more
You're
talks from
welcome,
you.
Dr. Bindal.
Yeah, sir.
I'm very happy to that both of you uh, coordinated the lecture so well. Thank you.
Thank you, sir. Thank you so much. Okay, participants. So I'm sure you must have enjoyed this talk. So Dr. Yogesh, please stop the recording.
And sir, I must say, students are writing appreciation comments in the chat
I,
box.
I
Oh,
think
thanks.
sir is very
I'm
used to that.
really uh,
They enjoyed your session
thanks to
very
all
well.
the students. Thanks. Yeah.
So shall I end the meeting, ma'am?
Please, please.
Thank
Okay.
you, everyone. Okay. Good night. Thank you.
Good night, sir. Good night.
Thank you so much, sir. I'm just ending the
Thanks.
meeting now,
Yeah, thank
Okay.
you.
and
Okay.
we will meet tomorrow.